In this video, we will practice finding intervals of increasing, decreasing, concave up, and concave down. If you appreciate the content, please give it a like. Given a function y, the first step to finding intervals of increasing and decreasing is to find y prime. So term by term, y prime will be 3x squared, and then the power rule again is going to be negative 12x. The derivative of negative 15x is negative 15. The derivative of a constant is 0, so that's y prime. The next step is to find the critical values of y. That's where y prime is equal to 0 or where y prime is undefined. However, y prime is a polynomial and polynomials are defined everywhere, so we don't need to worry about this one. Finding where y prime equals 0 is going to require some factoring. So I'm going to begin that process now. I'm noticing that all terms are divisible by 3. So bringing out that 3, the remaining terms on the inside of the parentheses will be x squared minus 4x minus 5. And all this is equal to 0. This trinomial is probably factorable as a binomial times a binomial. X squared can only factor as x times x. 5 can only factor as 1 times 5. Inner plus outer must equal this middle term. To get a middle term of negative 5, I need a negative 5x outer and a positive 1x inner. Also, positive 1 times negative 5 does make negative 5. So looking at this factored form, we can see that y prime will equal 0 when x is equal to negative 1 because of this factor, and when x is equal to 5 because of this factor. So these are the two critical values which we will now use to make a sign chart, a y prime sign chart. Put the critical values in order from least to greatest across the top and make a row for each factor of y prime. Be sure to label the sign chart as a y prime sign chart. We need to decide whether these factors are positive or negative in each interval. The 3 obviously is always positive, so we can just put a bunch of pluses in the first row. Looking at the x plus 1 is equal to 0 at negative 1. So this is the only place where this factor might change signs. So we don't really have 3 intervals to test. We only have the left and the right of negative 1. X plus 1 is going to be negative to the left of negative 1, and this factor will be positive to the right. X minus 5 is equal to 0 right at x equals 5. This factor will be negative to the left of 5 and positive to the right. The overall sign of y double prime will depend on the number of negatives in each column. An even number of negatives means y prime will be positive. An odd number of negatives means y prime is negative. And all positives, of course, means y prime is positive. Hopefully you long ago memorized the graphical relationships between f, f prime, and f double prime. You should be able to write this chart from memory on a piece of scratch paper or in the margin for your next test or quiz. This will be very handy on the AP exam as well. What is important now is that f will be increasing wherever f prime is positive and decreasing wherever f prime is negative. That means y will be increasing on the interval from negative infinity to negative 1 and on the interval from 5 to infinity, and y will be decreasing on the interval from negative 1 to 5. To justify the intervals of increasing, we say y is increasing on the interval from negative infinity to negative 1 and 5 to infinity because y prime is positive. Similarly, we say y is decreasing on the interval from negative 1 to 5 because y prime is negative. The concavity of y depends on the sign of the second derivative. So now we need to find y double prime, the derivative of y prime. Using the power rule, the first term will be 6x, and the derivative of negative 12x is negative 12. The derivative of a constant is 0, so that's it. This is y double prime. Normally, I would say we need to find where y double prime is equal to 0 and where y double prime is undefined. But this is a polynomial which is defined everywhere, so we just need to find where y double prime is equal to 0. Pulling out the common factor of 6, we have 6 times x minus 2 is equal to 0. Y double prime will equal to 0 when x is equal to 2. This is the only critical value. Your y double prime sign chart should be set up like this. 6 will be positive in every interval. X minus 2 is equal to 0, right at 2, obviously. It will be negative to the left and positive to the right. Y double prime will be negative in the first interval and positive in the last interval. Y will be concave up wherever y double prime is positive, and y will be concave down wherever y double prime is negative. So y will be concave up from 2 to infinity and concave down from negative infinity to 2. You justify your answer by saying y is concave up on the interval from 2 to infinity because y double prime is positive, and y is concave down on the interval from negative infinity to 2 because y double prime is negative. A point of inflection is where y changes concavity. We have learned that y will have a point of inflection where y double prime changes signs. So y will have a point of inflection at x equals 2. We say y has a point of inflection at x equals 2 because y double prime changes signs. Let's use the above information to sketch the graph of y. First, let's divide the graph into intervals based on the critical values -1, 2, and 5. Let's label y as increasing or decreasing in every interval. We can use the fact that y is increasing from negative infinity to -1 and 5 to infinity to label these intervals, and we can use the fact that y is decreasing on the interval from -1 to 5 to label these intervals. Now let's label every interval as concave up or concave down. Y is concave up from 2 to infinity and concave down from negative infinity to 2. In other words, y is concave up in these two intervals and concave down in these two intervals. In addition, we know that y will have a horizontal tangent line wherever y prime is equal to 0. Remember, y prime was equal to 0 at -1 and 5. Let's put little horizontal lines at -1 and 5 to remind us to form a horizontal tangent line at these values when we draw the graph of y. In the first interval, we need to sketch y as increasing and concave down and rounding out at a horizontal tangent line. So here we go, increasing, concave down, and rounding out at a horizontal tangent line. In the next interval, y is decreasing and concave down, and no horizontal tangent line is coming. So decreasing and concave down, and not necessarily a horizontal tangent line. On the next interval, y is decreasing and concave up. I didn't leave myself enough space, so I'm going to move this whole thing up a little. Decreasing, concave up, and finishing out at a horizontal tangent line. So here we go, decreasing, concave up, and rounding out at a horizontal tangent line. In the last interval, y is increasing and concave up. So we can just finish out as increasing and concave up. And that's it. For this next one, be aware that we do have a domain restriction. X is greater than 0. The first step is to find y prime. The derivative of 20 is 0. The derivative of 24x squared is 48x. And the derivative of negative x to the fourth power is negative 4x to the third power. Let's go ahead and write this in factored form. I see a common factor of 4x. So let's pull 4x outside of parentheses. That's going to leave us with 12 minus x squared. Y prime will equal 0 when 4x is equal to 0, or when 12 minus x squared is equal to 0. Dividing both sides by 4, we get x equals 0 from the first equation. Adding x squared to both sides, we get 12 is equal to x squared. Taking the square root of both sides, normally I would say x is equal to plus or minus the square root of 12. But we had that domain restriction. X must be greater than 0, so x is simply equal to positive square root of 12. Let's go ahead and set up that sign chart with our only critical value of radical 12, because the x equals 0 is the border of the domain restriction, which is actually 0 itself is not actually included. So radical 12 goes here on the sign chart. Don't forget to label the sign chart as y prime and put a row for each factor of y prime. We need to decide whether these factors are positive or negative in each interval. 4x will be positive in both intervals because we are talking about values of x that are greater than 0. 12 minus x squared is equal to 0 right at the square root of 12. If we plug in a test value that's less than the square root of 12, for example 1, this would be 12 minus 1, which is positive 11. So 12 minus x squared will be positive in this interval. 12 minus x squared will be negative for values greater than radical 12. For example, consider the test value of 4. If you plug in 4, you're going to get 12 minus 16, which is negative. Overall, y prime will be positive in the first interval and negative in the second interval. So we know that y will be increasing from 0 to radical 12 and decreasing from radical 12 to infinity. We say y is increasing on the interval from 0 to radical 12 because y prime is positive. And y is decreasing on the interval from radical 12 to infinity because y prime is negative. Before I go on, a brief word about abbreviations. In other videos, you will often see me abbreviate the word increasing like this, decreasing like this, because like this, concave up like this, and concave down like this. I accept these abbreviations in my class, but I need to be clear. You are taking a risk whenever you use abbreviations on the AP exam. That's because it's up to the discretion of the grader whether or not they're going to give you credit for these abbreviations. Now, most AP graders will give you credit for these, but there are hundreds of AP graders every year, and you never know when you're going to get that one grader that's not going to give you credit for something. So if you want to be 100% safe, do not abbreviate at all on the AP exam. However, if you are in a hurry, if you're pressed for time, it might be worth the risk. For intervals of concavity, we need y double prime. The derivative of 48x is 48. And the derivative of negative 4x to the third power is negative 12x squared. These are both divisible by 12, so let's factor out a 12. That's going to leave behind 4 minus x squared, which factors further as 2 plus x times 2 minus x. This is the difference of two squares. Looking at the factored form, we can tell that y double prime will equal 0 at x equals negative 2 from the first factor, and at x equals positive 2 for the second factor. However, we do have the domain restriction that x must be greater than 0, so that wipes out the x equals negative 2. So we only have one critical value with which to build the sign chart. So we will put our x equals 2 at the top. Make sure to label your sign chart as y double prime. We need to decide whether these factors are positive or negative in each interval. Obviously, 12 is always positive. And for values of x that are greater than 0, 2 plus x will be positive. Now, 2 minus x is equal to 0 right at 2. For values of x that are less than 2, like 1, for example, we're going to get a positive number. Think 2 minus 1. But for values of x bigger than 2, like 3, we're going to get a negative number. The overall sign of y double prime, looking at all of these positives, will be positive in this interval. The single negative makes y double prime negative in this interval. We know that y will be concave up wherever y double prime is positive, and concave down wherever y double prime is negative. So concave up from 0 to 2, and concave down from 2 to infinity. To justify, we say y is concave up on the interval from 0 to 2 because y double prime is positive. And y is concave down on the interval from 2 to infinity because y double prime is negative. We know that y will have a point of inflection wherever y double prime changes signs, which happens at x equals 2. We say y has a point of inflection at x equals 2 because y double prime changes signs. It's time to use the above information to sketch the graph of y. First, we divide the graph into intervals based on our two critical values, radical 12 and 2. By the way, we know that radical 12 is between 3 and 4 because 3 is the square root of 9 and 4 is the square root of 16. Let's label y as increasing or decreasing in every interval. Remember, y is increasing from 0 to radical 12 and decreasing from radical 12 to infinity. Now let's label y as concave up or concave down in every interval. We know that y will be concave up from 0 to 2 and concave down from 2 to infinity. In addition, let's indicate where y will have a horizontal tangent line. Y will have a horizontal tangent line at x equals 0 and x equals radical 12 because these are the two places where y prime equals 0. Let's put little horizontal marks at 0 and radical 12 to remind us to form a horizontal tangent line at these values when we sketch the graph of y. I'm going to start the sketch of y with an open circle because 0 is not included in the domain. X must be greater than 0, so open circle here. We are starting out at a horizontal tangent line, and then in this interval y is increasing and concave up. So here we go, increasing and concave up on this interval. In the next interval, y is increasing, but now concave down. And we need to finish out the interval at a horizontal tangent line. So here we go, increasing, concave down, and rounding out at a horizontal tangent line. We finish the graph with an interval that is decreasing and concave down. So decreasing and concave down. And that's it. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.